that affect resistance of a substance. We saw earlier that the resistance of a resistor in a circuit is given by the relationship R equals V over I. As the resistance increases, the current decreases. Current is inversely proportional to the resistance. Rearranging the terms, I equals V over R. There are two main factors that affect the resistance of a resistor: length and area of cross-section. Let us conduct an experiment to understand the effect of these factors. Consider a circuit having a cell, an ammeter connected in series, and a plug key. On a board, we have connected 4 different conducting wires. The first 3 made of nichrome and the 4th made of copper. The second wire has a length that is double that of the first wire and has the same cross-sectional area. The third wire has the same length as the first wire, but has half the cross-sectional area. The fourth wire has the same length and cross-sectional area as the first wire, but is made of copper. Any 4 of the wires can be connected to the circuit. For simplicity, let us assume that the cell has no internal resistance. Hence, its terminal potential difference is the same as its EMF. The first wire is connected to the circuit and the key plugged in. We observe that the current in the circuit is 200 mA, as shown by the deflection of the ammeter. The resistance can be found. When the first wire is replaced by the second wire in the circuit, we see that the current is halved. The resistance has been doubled. When the second wire is replaced by the third wire in the circuit, we see that the current is 100 mA. The resistance has been doubled when compared to the first wire. When the third wire is replaced by the fourth wire in the circuit, we see that the current hits the maximum on the scale of the ammeter, meaning that the current is beyond the scale. The resistance has been significantly reduced. We can conclude that the resistance of a conductor is directly proportional to its length. R is proportional to L. This is because the greater the length, the greater the number of positive ions that resist the flow of current. Hence the resistance increases. We can also conclude that the resistance of a conductor is inversely proportional to its cross-sectional area. R is proportional to 1 over A. This is because the greater the cross-sectional area of the substance, the greater is the area available for the electrons to move. Note that the number of positive ions also increases when we increase the cross-sectional area, but the increase in ions is smaller compared to the increase in the space available for electrons to flow. Hence the resistance decreases. Finally, the resistance of a conductor also depends on the type of material. Copper is a better conductor than nichrome, and therefore has a lower resistance to the flow of current.
Starting to feel it? Now go master it with Maxine.